Welcome to this explainer. We're diving straight into the mathematical architecture of the physical world today by taking a journey through electrostatic potential and capacitance. We'll be moving step by step from the behavior of a single isolated charge all the way up to the complex mechanics of energy storage. If you really want to understand the derivations that make electrostatics tick, you are absolutely in the right place.
Here is our roadmap for today. We'll hit potential versus difference, point charge potential, the electric dipole, field and potential, equipotential surfaces, and finally, capacitance.
Let's get right into section 1, potential versus potential difference.
Okay, so the contrast between these two foundational ideas is actually pretty fascinating. Potential difference, that is highly practical. It deals with two known locations. It's literally the amount of work you have to do per unit charge to move a test charge from point A over to point B, pushing against an electrostatic field. But electric potential? That brings a charge in from the great unknown. It asks a much more abstract question: how much work does it take to bring a charge all the way from absolute infinity, a place where the influence of other charges is exactly zero, to one very specific point in space?
And that brings us to our unit of measurement, the volt, named after Alessandro Volta. Mathematically speaking, 1 volt equals exactly 1 joule of work per coulomb of charge. Think of it like this: if you have to exert 1 joule of raw mechanical energy just to force a single 1 coulomb charge through an opposing electric field, you have exactly 1 volt of potential. It's a perfect, elegant one-to-one relationship.
Moving on to section 2, deriving point charge potential.
Let's actually prove this mathematically. Imagine you are pushing a tiny positive test charge toward a stationary positive point charge. The infinitesimal amount of work you do, dW, is just force times distance, dx. Now here's the crucial part. We multiply by the cosine of 180 degrees. Why? Because you're pushing forward while that repulsive electrostatic force is pushing backward against you. That gives us a negative sign. To find the total work, we integrate this expression from infinity all the way down to our target distance r. Since the electric force relies on a 1 over x squared relationship, integrating that gives us negative 1 over x. The two negatives perfectly cancel out, and when you plug in infinity as a limit, that term just goes to 0. What we're left with is the incredibly elegant formula V equals K times Q divided by R.
So, the absolute biggest takeaway here? Do not mix up your denominators. It happens all the time. Electric field and force, those are inverse square laws. But potential is an inverse distance law. It relies strictly on r, not r squared. Grasping this distinction between a vector field and a scalar potential is absolutely vital when you're dealing with spatial physics.
All right, section 3, potential of an electric dipole.
Now that we have single charges down, what happens when we pair them up? For any general point in space at an angle theta, a dipole's potential is negative k times the dipole moment p times the cosine of theta, all divided by r squared. Watch how beautifully the geometry works out here. If you are directly on the axis, theta is 0. The cosine of 0 is 1, so we get the maximum possible magnitude. But look what happens on the equatorial plane where theta is exactly 90 degrees. The cosine of 90 is 0. Physically, this makes total sense because any point on that equator is exactly equidistant from both the positive and the negative charge. Their potentials perfectly cancel each other out, which mathematically guarantees that moving along a dipole's equator requires 0 work. None at all.
Next up, section 4, the field and potential relation.
Let's bridge the gap between these concepts mathematically. A tiny amount of work, dW, is equal to negative force times dx. But force is simply our test charge, Q0, multiplied by the electric field E. Separately, based on our new definition of potential, we know that dW also equals Q0 times a tiny change in voltage, dV. So what happens when we set these two expressions equal to each other? It's pretty great. The Q0 charges beautifully cancel right out of the equation, and we are left with E equals negative dV over dx.
You need to sear this rule into your brain. That negative sign we just derived isn't just some mathematical quirk. It dictates physical reality. It literally tells us that in the direction of the electric field, potential drops. The field lines always point away from areas of high potential and point directly toward areas of low potential.
And because of this exact relationship, our units actually evolve. Instead of strictly measuring the electric field as newtons per coulomb, we can now define it as a potential gradient. Since E equals dV over dx, we unlock a new, highly practical unit, volts per meter. It tells you exactly how fast the voltage is dropping over a specific physical distance. It's a real game changer for visualizing how the field behaves in space.
Moving along to Section 5, equipotential surfaces and energy.
Let's scale things up from points to continuous planes and spheres. If a surface has the exact same voltage everywhere, the change in voltage, delta V, is exactly zero. Since work equals charge times delta V, moving a charge anywhere across this surface requires zero work. Now, if it requires zero work, the electric field cannot be pushing against you. This means the field lines must mathematically be strictly perpendicular to the surface at all times. Furthermore, think about this. If two equal potential surfaces were to ever intersect, that exact intersecting coordinate would have to have two different voltages simultaneously, which is of course mathematically impossible. No logical paradox is allowed here.
So, take a look at the electric field inside a hollow spherical conducting shell. It is perfectly zero. This is a brilliant result, proven by Gauss's law, because all the excess charge rests entirely on the outer surface. Now, since our equation states that E equals negative dV over dx, if E is zero, then the change in voltage dV must also be zero. This does not mean the potential drops to zero inside. Rather, it means the potential remains completely constant throughout the interior, perfectly matching whatever the voltage is on the shell's outer surface.
Now, as we know in physics, conservative work is never just lost, it gets banked as potential energy, denoted by U. Let's look at how this builds mathematically. To find the energy of a dipole situated in a uniform field, we calculate the exact amount of work done to rotate it. Work is simply the integral of torque over a change in angle. When we integrate torque, which is the dipole moment P times the field E times the sine of theta, we get a negative cosine function. Evaluating this integral between two distinct angles gives us the banked potential energy. So U equals P times E multiplied by the difference between cosine theta 1 and cosine theta 2. All that mechanical work you did? It's stored right there in the system.
Finally, we arrive at Section 6, Introduction to Capacitance. So, how do we practically capture, hold, and utilize all this theoretical electrostatic energy? That's capacitance. Defined as C equals Q divided by V, it measures how much charge a body can essentially hoard per single volt. The absolute crucial point here is that capacitance depends purely on physical geometry, things like the surface area of the conducting plates and the physical distance between them, which we see in formulas like C equals epsilon naught times A over D. It does not depend on the actual charge or voltage you apply. Think of it like a bucket. The bucket's physical capacity doesn't suddenly change just because you decided to put less water in it.
We measured this capacity in farads, named after Michael Faraday. But here is a staggering mathematical reality to wrap your head around. A true 1 farad capacitor built out of basic spheres wouldn't just be big, it would be literally larger than the entire Earth. It is a massively huge unit. Which leaves us with a provocative thought to end on. If 1 farad is virtually impossible for everyday objects, how on earth do the tiny, microscopic capacitors crammed by the billions into our smartphones pull off this incredible physics trick to store so much energy? Think about the mind-bending material science and geometry required to make that happen. Keep that curiosity firing until our next explainer.